Welcome to Flat Earth Debate. I'm your host, Nathan Oakley, and if you are new to this channel, or you're amongst the 50% of the people watching this who have not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. If you would like to support this channel, there is a super chat that runs alongside the show while it is live, and if you would like to join the debate, there is a link in the info box below this video. With the page you are watching me on now muted, simply click that link to join the discussion and express your views on the shape of the Earth. There are a couple of rules in the Hangout. Number 1, please do not swear. If you do, you will be ejected, and if you are, please do not try to rejoin the stream using sock accounts. You will be warmly welcome back on the next stream. In a moment, I'm going to transition across to my photo so I can share the show on social media, and I would encourage anybody who is in the live audience to please do the same. Sharing is possibly the most important thing you can do, as it increases the live audience, which in turn increases the chances of a more diverse panel. So please share the show. One last time, if you are new to this channel or you have not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth Debate. Try and do this at the same time as I do a few shout outs. Quite a few people here already in the chat by the looks of things. Scooby-Doo, good to see you. Thanks for being here. Daylight, Ohio, good to see you, sir. Thanks for being in our chat. Paul, contributor to the show. If I could get my tongue around it. Good to see you here, Paul. Hopefully we'll hear from you tonight. Miles Davis, same applies. Good to have you here, Miles. Nice to see you. Shill Scanner says MK Ultra is the best drug ever. Is that so? I'm sure it is. Leather Chaps, Fap King Dong, Shaven Bunghole. Good to have you in our chat. Excellent screen name. Very creative. Eastern Hemisphere, nice to have you here. While I'm doing these shout-outs, if one of you from the chat could just click the link. Ah, perfect timing. Perfect timing. We've got Paul, Curved, and P. Mars all at the same time. So let's raise the mic on the Hangout and do a few introductions. So if we start with Curved Water, as you were here first. How are you doing, Curved?
Very well, thank you.
Good to have you here, sir. And Paul, how are you doing, Paul?
Yeah, good. I'm a bit tired. I've been up all night doing calculations and stuff, so I'm ready to roar.
Excellent. That's good to hear. And last but not least, Paul, P. Mars, how are you doing?
Yeah, I'm good. I'm about to hit the gym. I just want to drop in and show you how beautiful I am.
You're looking buff, Pop. You're looking buff, P. Looking good, looking good. Right, well, I'm going to go on mute. Hopefully you two will have a reasonable discussion, even though you're pretty much all on the same side. I know P's dropped already. There we go. I'm sure I've seen some chat that was going by in the chat feed that could be continued. Oh, no, Pete Shea. Possibly a troll Pete Shea. Oh, damn, missed him.
Hey, I'm a real boy.
How you doing, Tony? Good to have you here.
How you doing, Nathan? I just shared too to like 500 people, so I did my job today.
Thank you so much. I really appreciate it, honestly. I'm not just saying that. I really, really do appreciate it when you share the show.
I know you. I know.
I
This is good entertainment. This is good, wholesome entertainment. Good for the whole family.
If you don't swear, yes.
What's up, Paul? How you doing, man? How you doing, Paul?
Yeah, I'm doing good. I'm doing good. Yep.
Hey, Paul.
So you ready to debate Riley? He's got some real good evidence for you.
Has he?
All right, I can't wait to.
Well,
I got my popcorn ready. I'm ready.
Different. That'd be something different.
I haven't seen him in the chat. I hope he comes. He may not come.
Yeah, Riley was trying to get a hold of you earlier, asking for how to get a hold of Paul. He had something to show you.
Okay.
Yeah, I tried getting a hold of you in Hangouts, but I don't have you. So I just did like a group message to you, but you obviously didn't see it.
No, I've got to sleep sometimes.
But get ready to answer questions about the core.
Oh yeah, yep. About the core or about minerals mined from the bottom of the Cola Deep.
Yes, that's good. You're right. That's a good point.
Which is nowhere near the core, nor is it under the temperatures or pressures of the core, and neither is it liquid molten iron. That'll be interesting.
Yeah.
I think another point to make is that everyone makes mistakes in calculations every now and then, and that's a point that I'll be certainly bringing up today.
Were you able to determine who it was that was doing those calculations?
I certainly was able to determine who it was doing those calculations. Yeah.
Okay. All right, good.
Yeah.
Who was it? Name names.
Hector.
Who's Hector? Sorry, I don't know who Hector is. I heard his name mentioned. Oh,
Hector
Talk of the Devil.
Hector is one of Geo's friends.
Oh, okay.
Alex's friend.
He's a physicist. Here's Anthony.
Yeah, I'll do a quick introduction if I can get my mouse to go over my camera. How you doing, Sleeping Warrior? Good to have you here.
Good morning. How are we all?
Very well. We've also been joined by Alex Cat Earth. How you doing, Alex?
It's going to be epic.
Sorry.
Riley's got... it's going to be awesome.
I think I heard you. And Truth Seeker as well. How you doing, Truth Seeker?
Someone's doing something in the background funny.
We've also been joined by the Rumpus. How you doing, the Rumpus? Good to have you here as well. Sorry about all the noise.
The Rumpus makes us laugh too.
Big shout out to Scooby-Doo for the super chat. Thank you very much, Scooby-Doo. Good to see you.
This is going to be a good one. This is going to be a humdinger. All right.
We've also been joined by Lewis Hackett. Good to have you here, Lewis. Again, sorry for all the noise.
Yeah, I've got a presentation on this angle thing, if you're interested, on this, because I've seen all these claims about you not being able to determine the distance of things. And I've got a little graphic I've sort of worked out and things for people to look at if they're interested.
Sure. Fire it up.
Yeah, I got a quick question. How can't you tell that the object's half the size and twice the distance away? Angular size will say the both for the same object.
Correct.
That's right. It can, yes. But I'll just demonstrate how you can determine the distance of things.
While you're bringing that up, the Rumpus, I'll just say one last intro. I think we've got a full house now. I've been joined by Part-Time Vegan, who generally needs turning up. How you doing, Part-Time Vegan? Good to have you here.
Can you hear me?
We can indeed. I've got straight on the case and got you right up. So yes, we can hear you.
What up, PT?
What's up, Curve?
Unbelievable. We are 6 minutes in, full house. Amazing. Good to have you all here.
Yeah.
So shall I get on and show how you can do these things?
You're on. You're being presented, Rumpus.
Go. Okay. Can you see my screen?
Yeah. Yep.
Great. Right. Okay, so I mean, people like Nathan and I must admit a few others seem to think that you can't determine the distance of something without actually sort of going and sitting on it or something, and you can't determine it remotely from a distance without having to go and sit. And there are a number of ways of doing this, but this is a simple one that you could do. Anybody could do with just a simple, some simple tools. So the only tools you need to do this. So here, for instance, here we're on an island. Here's an island on a sea. So we can't go over to the island that is up here. And we want to know what this distance D is. And so we're O, the observer, and this is what we want, the distance we want to work out. And the only things we've got are a compass and some means on the compass, you know, when you go orienteering or something you can measure the angle relative to north or something. That's all you need, plus an odometer, in other words, something to measure how far you walk or travel. And so, right, so here's the situation. And a number of people said repeatedly in the last few, and I've seen very many of these, but seem to repeatedly said you can't determine the distance of something. You know, it's impossible. And let's just go into this. It's simple trigonometry. A sort of 13-year-old could do this, but let's just go through it. And then I'll also demonstrate how you can determine the height of things above the Earth, which is a bit more tricky. But anyway, let's do this simple one with an island. So here we are, an observer on an island, and we want to know how far this other island is away. Okay, so what we could do, one simple way of doing it, is to first of all get an angle look at the island, get an angle on that, and then say, right, let's go 90 degrees to the direction of the line of sight, and just go 90 degrees to that, walk a certain distance, X, then have another look at the same point you were looking on the island, and you get an angle. And anybody with basic trigonometry skills should realize that tan theta here is equal to d over x. So therefore, as we know x, and we know theta, just rearrange this. So here's the equation, tan theta is equal to d, it's basic tangent. So if you know, rearrange the equation to put d, so whip over x over here is the unknown. We've got two knowns now, and one unknown, d. But we know x, we've walked that distance, and we've got the angle theta, so there we have it. We've done it. We've now determined where that island is without having to visit it, just by having the distance with a right angle triangle. The only thing you need to know is two things about it. And here we've got a theta and one side. Now, so that's one way of doing it, but you might not necessarily be able to. For instance, if you were stuck, if you're over here, further to the right when you wanted that, you might not be able to go to 90 degrees. So it becomes a bit more problematic. So, okay, let's consider a more tricky situation. Whoops. This time we're an observer at A. You can see my pointer, can you?
Yeah.
Great. So here we've got a pointer at a position at A, and we can't go at 90 degrees because we go off into the water or something, or perhaps there's a tree in the way or whatever. But we can still get a sight. We still say, well, that's the angle to the thing off north. And then we walk to somewhere else over to point B, and then we have another look. And we take another sighting of it. But we know how far we walked. In this case, by the way, the uppercase letters, as is usual, means angles. Lowercase means distances. So all we've done now is we've now got two angles and the distance. And if you use the sine rule, which is up here, we need to just measure A, B, and C. So again, we haven't gone into the water, we haven't gone over to the island, and use the sine rule, which is C over sine C. In other words, it's this distance here over the sine of the opposite angle is equal to the ratio of another distance over its opposite angle. And if you just rearrange this and you work out C, from any triangle, it's 180 degrees. So you can work, having got A and B, you can work out what C is. So using the sine rule here, you say C is equal to pi. This is in radians, by the way. If you're not happy with radians, that means 180 degrees, because of course the sum of a triangle's internal angles is always 180 degrees. So you can work out what C is from pi minus A minus B. So those two angles there, you know, you can work out what C is. And then you can say, right, I can then work out from just rearranging this, you should be able to see that I can just rearrange this. If I have, there's A, if I move this sine A over to this part of the equation, I'd end up with this equation, which means I then have A, which is this distance here, is equal to C, which is the distance I measured when I walked or whatever, sine A divided by sine C, which are the two angles I know. So again, even in this situation where I can't generate a right angle triangle, I can still determine the position of that by having a moving along certain way and then taking another sighting.
Can I ask one question?
So very
Rumpus?
easy. So very easy to do. You can work out distance to a tree, anything like that. So you can work out distances to things without having to go anywhere near it.
Can I just ask one question? Thank you for that, Rumpus. That was excellent. Just one question.
I've got okay. I want to develop this, but yeah, what's the question?
So above C, there's a dot.
Yeah, that's the point you're looking at. That's all I've just drawn. That's the focus of where people want to know on the island they're looking at.
And can we do that with the sun? Is there just one particular point that we use? Is there?
Well, this is a plan view. Of course, it gets a bit more tricky on the Earth. I'm about to do that now.
Just before you ignore my questioning completely, Rumpus, with the sun, is there some reference point on it, some landmark on it that we can use?
Well, you could just take a look at the bottom of it if you wanted to.
You could take the bottom of it. You say.
You could do that, yeah, or the top. You from this is a plan view, so this is a little bit different. This is
Sorry, just to answer my question. Just before we go any further, I just want to get that clear. Is there a particular point on the sun that we use, like you've picked an arbitrary point on that island?
You could use a sunspot.
Yeah, I mean, you could use a sunspot. I mean, or you could just use the bottom. I mean, both of these people would agree.
Sorry, a sunspot's landmarks that we know what size they are.
Sorry, say again.
Are sunspots landmarks, like an equivalent of a landmark? Something we know.
Absolutely.
You know, they are.
Yeah.
They're
I mean,
based upon the observer.
But you could just use the bottom of the sun. I mean, in this particular section, you could everybody could see where the bottom of the sun is. You know where the curve is at a 0
Okay, Rumpus.
gradient. So
no problem. We could use the bottom. Okay, you carry on.
You could use the bottom if you want to, right? But it's a bit more tricky on a curve thing. So there we are. So that's demonstrating the principle. You do not need to go near things. You just need to have a distance. But with a triangle like this, you need 3 pieces of information. The one on the right, you need 2 angles and a distance. For a right angle triangle, you just need 1 angle and a distance. But okay, let's now look at the much more tricky situation of measuring the height of something above the Earth. Right. So here we have
got an arbitrary point on the bottom anyway. That's handy.
Right. So this is the moon I happen to be dealing with here. So you could be looking at a crater if you liked. Here we've got one telescope, and this is the angle that someone's looking at up at it, one observer. And here's another observer with another telescope looking at it, looking at the same crater, whatever. And we want to find the value of h. So we want to find the distance to the moon from the Earth without having to go anywhere near the moon. And we know the distance between the 2 observers on the Earth. So we've got 4, and we've got a 4th piece of information. We've got the radius of the Earth. So with these 4 pieces of information, that's all we need to do to determine the distance to the moon from the Earth. Right. So how are we going to do that then? It's not trivial. Tell me if I'm taking this too quickly or it's too involved or whatever. So let's get. So here, let's just reduce that to the angles. I've removed the telescopes and things. This is what the eventual equation will look like here. That's the answer, where x represents this thing, and r is the radius, and s is the distance between the 2 points. But I'll now do the construction. I'll now bring in the construction lines to show you how it works. Right. So again, the only observation here of A being the angle from one observer to some point on the moon, and B we have the other observer and just the distance. We want to work out h. So how are we going to do that then? Right. The first thing to do is to say, right, we're on the planet Earth, and we know these radius lines come from the center, and they hit the angle above the horizontal. They're going to hit this at 90 degrees. So these angles are above the horizontal, and we know the horizontal is a tangent to the Earth, and therefore that's 90 degrees to the radius. Okay, so we've got a little bit more information now. So what we want to do now, we've got a slight problem. We don't have we can't use the sine rule here because we don't have all the angles that we need and the distances. The only distance we know at the moment is this distance r and the distance s. Now you can see here that we've got a triangle. If you follow my pointer, this triangle here, there's the height we want, and we can see that the height plus the radius is this side of the triangle. So if we could work out, this distance here, as well as this radius here, and this angle here, which I will now bring up. So if we could work out,
how can you be sure? How can you be sure the 2 observers are lined up in the exact same line of the triangle?
That's right. Good point. Good point. Yes, that's a very good point. Now I didn't mention that. For this particular situation, you do need the 2 observers and the moon to be in the same plane. Now we actually did an experiment with this. Someone arranged this looking at the ISS. They waited, and the 2 people waited until the ISS was on a line between them, and so this equation is only valid for when all these 3 points are in the plane. So this is, so it's not the full 3D one, but it gives you a flavour of how to go about it. I haven't done the full 3D one.
Sorry to sound stupid, Rumpus, but on a line, I don't really know what you mean. Can you just explain what you
mean?
Right.
Okay. So okay, very good point. I didn't make this clear. I did actually meant to this. Right. So the moon here, the object you're looking at, and the 2 observation points have to be in a plane. In other words, you don't want the moon to the right. So if you were to draw a line between the 2 observers, this equation I'm presenting won't cope with the moon being, into the screen or further out away from the screen. So they have to be in a plane. Do you understand that? Have I made that clear?
Yep, that was my point.
Yep, so you made a very good point, and I meant to mention it actually. So well interrupted that, whoever that was. I can't see who it was, but interrupted.
I'm sorry to interrupt again, Rumpus, but can you explain what situation you have where 3 points cannot lie in a single plane?
Well, okay, the plane. Sorry, you're absolutely right. Good point, Curve. The plane has to go towards the center of the Earth. So the plane actually is defined. So it's actually 4 points actually. I should make that clear. So it's the point here, the point here, the point here, and the center of the Earth all have to be in the same plane. So yeah, good point, Curve. Well spotted, that man. And as I say, someone did an experiment when the ISS. They made sure that they did them observations when the two people had a line, the line directly joining them, and then when the ISS, was directly above some part of that line between them, they then did the observation. And then I actually used this equation when they offered me the information that they had. They gave me the two angles, A and B. So they gave me A and B and told me how far they were away from one another. And I used this equation, and I ended up with the ISS within 500 meters. So obviously they made a very good observation. So we know this equation works. It's actually being used in the real world. And also George Natayuk as well. George Natayuk and I both had a go at deriving this. We ended up with the same result. So we know that equation is correct. So let's derive it though. If you're interested in the derivation, if people are getting bored, just let me know and I'll stop. Right. So we want to find this angle G here, and then we can use the sine rule, which we used before, and the cos rule, which is another rule I'll bring in a minute. But we need this angle G, and we need to know this distance here, which we don't know at the moment. So we've got a bit of work to do. Right. So knowing that these points are on a radius here, and these points are horizontal, and these are 90 degrees, we can then make a few more. All right. Yes. So we're trying to determine B here. Oops. Stop that. We are trying to determine B, and we need to determine the angle C. Just as up here, we needed to determine the angle C. We did it by subtracting pi, which is 180 degrees in radians, from these two, A and B. So we need to do the same thing down here. So we need to determine B and C, and I don't think actually we need to determine A, but we certainly need to determine B and C. Right. So next thing we need to do, we then draw a chord between the two observer points here, and we then take the halfway point, and we know because it's a halfway, because we decided the halfway point, that's going to be a right angle, and we know this angle here D because we know the length S, the distance between them. And if you are familiar with radians, you'll know that the angle in radians is equal to S over R. So just simply take the distance S that separates them, divide by R, and you end up with this angle down here, D. And if I half that angle, which means I then have a triangle with this angle as being D over 2, I know this distance R, and I know this is half. I then, from that right angle triangle, I then know D over 2, and I know R, so I can just use simple trigonometry to work out that's R sine D. Actually, that half is R sine D over 2. So this angle here that I worked out simply from saying S over R, which I had over here, I just simply then said, right, use trigonometry, I've got R sine D over 2 gives me this length here. If I know that's that length there, then I can then double it, and I can get the value of C. So I now know the length of this chord, which is from here to here. So I now know this length now, extra information. Right, next point. I now need to know what I'm trying to do is I'm trying to get this K and L angle. If I get just like I did in the first example, if I knew K and L and I know C, then I can determine little c distance. I can then determine the big C angle. So what can I determine K and L? Well, if you look at this, this is the angle A here, which is the observer's angle to the moon. And so if I knew what J was, then I can just simply add A and J, and then I get this angle K here, which is the internal angle over here of this triangle. But of course, I do know what J is because I know, where's H gone? Because J here is simply equal to 90 minus this angle. And I know this angle from the fact that it's part of this triangle here. And I know that this is D over 2. I know that's 90 degrees. So therefore, I know that H is 90 minus D over 2. So I then know H. So if I know H, I can then say 90 which is this angle here, minus h gives me j. If I now know j and I know a, I then know k. So now I know k, and I can do the same on the other side. So I now know k, and I know c, and I know l, which is exactly the same situation for the cos rule here. So I now know this angle, and this distance. And I can work out that angle in the same way as I said before. Because it's a triangle, I can just simply take 180 minus this angle gives me that angle. And then from that, I can use the sine rule to work out what b is. And here, so I've got b is equal to c sine b over sine c. And as I said, we know c, we know b, we know c, so I can work out b. Great. So I now know b. Right, so now I know b, and I know r, and I know this angle here, g. So now I want to work out what this line here is, h plus r, and I can do that with the cos rule, which is this. The sine rule you need, you use when you've got two angles known and one side known. You use the cos rule when you've got two known sides and one angle. So, you know, in one case you've got two angles and one side. In the other case, you've got two sides and one angle. And this is the cos rule. And if you just twist that around a bit, so what we're trying to do is to establish that you can think of this C here is G here. So what we're trying to do is to determine C here. So if you turn this angle 90 degrees, you'll have this triangle here. So we know A and B here are B and R. And then we're trying to determine C. So we then have this equation, c squared is equal to a squared plus b squared. So we know all these elements, including the angle c, we worked out. And so then you have to get into, so having established that, we then know the formula using the cos rule, and that is represented here. It's this equation here. So this represents how I derived all those angles that I've been describing to you here. There's the sine rule to determine the b. And here's the cos rule to determine the distance h plus r. So we know that. So we now know what that triangle is that sum together. So there's using the cos rule there. I mean, it's probably getting a bit involved here. If you're confusing you, please let me know. Then you can then start getting gets a bit algebraic confusion here. So we have the thing we want to find out is, whoops, don't do that. The thing we're trying to find out is this h here. And it's buried in this because it's c squared. So remember, this is the distance we're trying to work out, and it's c squared is equal. So there's and we know that's equal to r plus h. So we've got r plus h. So we need to square root the thing that's opposite. So we go r plus h equal to square root. Then finally, this is the equation. We end up with that. And then, but we've got all these other complicated terms like b squared and br and things. And then following quite a lot of algebra. Is where you make all the substitutions, where if you screenshot this and you're interested in going through it, you can see how there's some various substitutions. And then eventually you end up down here with that's the final equation in its full form, but you can simplify it because this bit is copied. That bit there, there, and there is the same as that bit there, there, and there, but it's squared in this case. So if you make the substitution, if you decide, so let's make this thing called x a substitution, the final equation then simplifies to that. So just from, and you can, all the information there is, which I then simplified up here to the final. I just made explicitly d, which is the angle using s over r, and then so all the information there is from we know s, which is the distance, we know r, the radius of the Earth, and then a and b is the observation angle of one angle, and a is the other. That's the only information you need to get to go through that. That's the substitution you make, and all the components in that equation do nothing more than use the four components that I mentioned up here. Those four components there are those four things in here. And so from those four little bits of information, we can work out how far away the moon is. If you on a line, so there's, as the chap who interrupted me initially, and curve follower are in a plane, you can do that. So with the ISS, it's a little bit easier because you can pick your time. You can say, you know two people, and you know when the ISS is going to be between you two. You can then go whack, make the observation. Then with the moon, it's a bit more tricky when you think it's directly in line with the person. But obviously, you could develop this equation further into a 3D version where you don't need to worry about it all being in a plane. But anyway, this will get you going, certainly, to measure, for instance, the height to the ISS. So there's absolutely no problems determining the distance to the moon. And you can do a similar thing with the sun. Although they might have the same angular size, they will appear to be different from the observer's point of view. They will have different angles to them. And from that, just as 17th and 18th centuries observers, they got to approximations of where the sun was. They had to do some little bit more tricky things like measuring the distance to Mars, and eventually they did it very accurately by using the transit of Venus. They were able to work out where the sun exactly was, and so you could measure the distance to the moon. You can measure the distance to the ISS with a PAL, and there we go. So that's it. Any questions, or did I confuse everybody?
No, I'm with you. First off, that was seriously impressive.
Oh, yeah, for real.
I'm sure everybody will be impressed by that, because I was impressed and I was watching it intently.
Good job, Rumpus. Good job.
I do have a couple of questions though.
Good. All right.
The value R in the equation relates to what?
The radius of the Earth.
Now, isn't that a presupposition that we live on a ball?
Yes.
If we did the trigonometry without the supposition we lived on a ball, how would the results differ?
Well, obviously, it would be a lot easier. I mean, I wouldn't have to make all this fiddling around trying to account for these angles here and adding it around. And but the point is, it doesn't work. If you do the calculations for lengths on a ball, and you take 3 observations, you'll find they're incompatible. They contradict one another.
Okay.
If you let's just draw another. Okay, so if you did on let's just draw. Let's get that moon up.
Well, maybe rather than showing me, maybe you could just. I don't need you to explain it, but what I would like to do is.
So if you let me just so now what people do say, for instance, they measure the sun and they say, oh look, if you do take 2 points and use the Eratosthenes trick, you end up with a distance of, I think, is it 3,000 miles or something? Can you do that?
3,000 kilometers, I think.
I think it's isn't it 3,000 miles? If you take the stick thing, so actually that should be the sun, not the moon. Though I think they get the same answer for both, don't they? Certainly the sun. So if you do this, you find I think it's 3,000 miles you end up with if you do the Eratosthenes and you assume that it's all on a flat. The trouble is, when you then take a 3rd observation, unfortunately, you end up with a different. If you then try and combine the results, it doesn't work, which should tell you can't be on a flat plane. That you can get a result with 2, but immediately you throw in a 3rd observation. So if you if you end up with an angle, so if you have an angle here of A, and an angle here of B, and then you say, we won't just do that. We'll actually ask Fred. Let's get this one here. C. You will find that it's incompatible. It doesn't work. The trigonometry says no, that can't be right. So therefore, you can reject the flat Earth simply by doing 3 observations, and you find that the angles don't agree. They do not end up at the same point. Karen?
Yeah. 3,000 miles only works if you're a little bit under 45 degrees of an arc away from the subsolar point.
Right. But the point is that what you will find is that if you're on a flat Earth, you take this position, you will find this 2nd observation here, when in fact, say, the angle to it is up
I'm sorry,
here.
could you repeat that? You're saying 3,000 miles is too close because what? What's the reason behind it?
Well, if you do the calculation and you simply say, you assume that the Earth is flat, you will end up, if you just take 2 observations, you will say, right, the sun or the moon, the sun or the moon will end up being 3,000 miles. But unfortunately, if you then throw in a 3rd observation of someone else, and you ask them to give you an angle, you'll find that they say it's up in, it doesn't agree with the other 2, and you cannot make it, and you cannot fix it.
Have you done the math to confirm this?
Well, I haven't done it recently, no, but I know that it will not work.
Has anybody done the math to confirm this?
Well, they know. Yes, people have done observations on the moon. They've given results. You can people give observations on the moon all the time. I mean, and you will find that those observations.
Can I interject there? Can I interject there?
Yeah,
Sly Sparkane did an excellent experiment. He got people to measure those angles all over the world.
It was brilliant, wasn't it?
And then what he did was he started with the assumption that the Earth was flat.
Yes.
And he showed that all of the lines drawn at the angles did not meet at any one single point. They crisscrossed everywhere and didn't end up meeting at a single point. And
brilliant point.
That when you take it to the sphere, all of the lines, every single one of them crosses at a single point. They all cross at the same point, giving the location of the sun. So he demonstrated that with an actual experiment of people taking measurements worldwide, actual measurements, and then he demonstrated that it doesn't work on a flat Earth, but that it does work on a spherical Earth.
That's a brilliant point, Paul. Absolutely brilliant point, Paul. That's absolutely spot on. He demonstrated from actual observations of doing exactly what the previous person who asked me a question has done exactly. Sly's done exactly that. Demonstrated that you end up with all over the shop, and only with a spherical Earth do you end up with them all pointing at the same thing. Great.
Can I get a link to that, please?
Great comment, Paul.
Yep.
Okay.
Do you have a link to that? Somebody, I think Part-Time Vegan wants to see Sly Sparkane's video. If someone has a link.
All right. So, Rompus, would you agree that if you calculated it based on the radius of the Earth, that you are using the presupposition that we live on a ball Earth? Yeah.
Yeah.
Are you aware of the video? It's quite old now, but it's one that is often cited by people in this discussion because it illustrates perfectly what you're showing on a spherical model applied to a flat Earth model and getting the opposing results. And the point of the video is that depending on what maths you put in, it governs the maths that you get out. So in other words, if you presuppose a ball, then you are on a ball from the maths point of view. Well, if you don't presuppose the ball, then you're not on a maths point. You're not on a ball.
Yeah, but as Paul just pointed out, Sly Sparkane got people to observations, and it doesn't work if it's flat, whereas it does work if it's on a sphere.
But the other thing that Sly Sparkane did also show is that all the ones that were not lining up on the flat model, they were all close. And they can be explained easily by human error.
No, that's not true. That's not true. They weren't even close.
Yeah, they were. Bar one.
All of them were close bar one. No, but also the point. There's this. We also know that this works because when I did this calculation with people who did observations with the ISS, they came out to within 500 meters of the known height of the ISS. So we know that it works.
What's the known height of the ISS?
Sorry. 405 kilometers high, and I think the result I got was within 500 meters of that. So the people who did the observation of the angles and telling me how far they were apart did a really good job, and they also picked the moment exactly right to make the observation of the ISS. And so it all confirms, all hangs. And that's the thing about we've got pictures of the Earth. We know we've had people up in the ISS. We know how high it is, and we've got some observations of people and hangouts that have done the observations. And my formula says that's where it should be. It all hangs together. It's all self-supporting from every single different direction. All these things interlink, all saying the same thing. It's only flat earthers who don't understand trigonometry who have the problem.
But do you at least agree that if you presuppose you live on a ball, the value for R means that you're going to get a ball result? In other words, if you don't presuppose you live on a ball, then you get a flat result. So how do you know?
That's the whole point. That's the whole point, Anthony. That's the whole point, Anthony. Is that the maths does not work unless you use a particular value for R. Exactly. And what that is doing is demonstrating that it must be a sphere for it to hang together and work.
That's right, because it gives the right answer.
It doesn't work if you use it flat.
If you wish to believe that demonstration is proof that we live on a sphere, then you can believe that all you want.
Well, there are other ways of measuring. Yeah, but hold on. But we've got other ways of measuring. I mean, this uses R, but we've got loads and loads of ways of determining. Just simply looking at was it the 13th century Persian? Just by going up a mountain and looking at the angle you have to look down. There's a very simple proof of determine the radius of the Earth. We've got pictures of the Earth. We can go and measure its radius. We've got just buying a boat going over the horizon. Even if you can even determine the radius of the Earth just by having something very horizontal. If you've got a theodolite and you make sure it's absolutely horizontal and you look over water, and you see how close the horizon is. You see there's a little gap. It doesn't quite come up to the horizon point. Just that tiny 0.1 degree. If you measure it accurately, you can also get a measurement of the radius of. So that we've got about 50,000 different ways of measuring the radius of the Earth. And we've got pictures of the Earth, and that gives you the value of R, which I've then used, and it then gives you the right value for the distance to the ISS. We've had people go up there, and we've got bouncing radars off the damn thing. We know exactly what it is, and all that information, all those things come together. If it wasn't true, if the ISS wasn't at that height, the Chinese would be going shouting, or the Russians or Mongolians or someone would be saying, look, I want a Nobel Prize. All these people have been lying all the time. All the information that's established and verified all agrees with itself, and my theory just put together, and again, it self-supports the radius of the Earth, because it wouldn't work. If that radius was wrong, I wouldn't have got the ISS to be the right height. And also, of course, we can tell the ISS is at a particular height simply by the your favorite thing, the angular size. If we know how it's been built, we get take the angular size of it. Therefore, we can then say, if we know what size it is, we know what angular size it should be, and it's that angular size. Therefore, we also know what height, size, how far it is away. And this information, and this point also supports that. So it all hangs together. Every single piece of information, scientifically derived, ends up with the right value.
But it's still based on the supposition that we live on a ball, and
but there's 5,000 different pieces of evidence to say that's the case. We have pictures.
50,000 before, but now it's
Anthony, if you start with the supposition that the Earth is flat and you get these measurements from all across the world, it will slowly, each and every measurement that you get will slowly point towards the Earth being a curved surface with the R value of what we've assumed here.
Boats going below the horizon, hull down, tell you they worked out this is where the ancient Greeks determined there must be on a sphere, because the goddamn boats used to disappear. You can see spheres the moon is spherical. You can bounce things off the radar off it.
Just to clarify, Rumpus, in them maths that you've just gone through there, just clarify with a straight yes or a straight no. Was there any consideration or adjustment for the atmospheric conditions that change our view?
No.
Perfect. So we'll come back to that later. Okay. But it was a good demonstration, mate. To be honest, I was like, I think I'm a chicken now. When I wake up, I'll become a chicken. Totally hypnotized.
Anthony, you set me a task. You set me a task last time to show where Hector went wrong. Would you like me to go through that now?
Bear with me. Let me just get my thing on screen so that we can work from somewhere.
Also, real quickly. Also, I keep hearing a whole lot about this map that works either way, depending upon what you assume about the shape of the Earth. I would like to see this video that everybody keeps referring to.
I've dropped a link in the side chat. Curved.
There's a link. I have no idea what channel or nothing.
My last message in the side chat, Curved.
Can you put it in Hangouts too?
I don't see it.
Oh, where's my message gone?
The Illuminati took it, like they always do.
23:31.
You see, as you get further away from a point on the Earth, the more deviation you will get in your visual angles. For example,
Now, I just want to make a point right here. If we're on the curved Earth, which, fine, let's say we're on a curved Earth, why is it when we fly, whatever, we don't ever see buildings leaning away from each other like this? And they have to, because certain parts of the Earth are curved away from others. So at some point when we're on a plane or we're on, some type of ISS, space station, when we're on something, at some point we've got to be able to see buildings that are curved away from each other. But we never, ever see that.
Jade were to look straight up in California, and I were to do the same in Florida, we would not be looking in the same direction. There is a deviation there caused by the curvature of the Earth. How do we correct for this? Simple. A complete circle is 360 degrees. So if we divide the circumference of the Earth by 360, we will get 69.169 miles per degree of change. Now, if we take the distance between our two observers and divide it by that number, the miles per degree of change, we find that our visual degree difference is 34 degrees. So what this means is that we will need to add 34 degrees to Jade's measurements in order to offset the difference.
Okay, so we need to offset the difference for the curvature of the Earth. So we're going to look at two ways. One is the Earth is flat, doesn't mean a pancake. You look with your eyes, you see that there are dimensions up and down to the Earth. We need to make note here for curvature of the Earth, and we're going to do that. But what if the Earth is flat? If it's flat, then we don't need to do this. So we're going to see what the two differences. Remember, Jainism said it's only about 3,000 miles away. And this guy says it's horseshit. If you use trigonometry, you'll see that is wrong. So let's find out.
Which, when we do the simple math, gives us a new value for Jade's observations.
So now Jade's observation, which she saw, was 55.4, right? 55.4. Like, nope, sorry, the Earth is curved. We gotta add 89.4 degrees. So we have to make it to where I'm at 90 degrees and you're at 90 degrees. Shy of 0.6. Let's keep going.
Value is 89.4 degrees. This means we can now find our parallax. Now the inner angles of any triangle will always equal 180 degrees. So
okay, so he brings us up that the angles in a triangle will add up to 180 degrees. So here we have angle 1. My formula up here up top. Let me pull this down a little bit. So you see that there's no formula in this box. Next box, no formula. And then this box, what I'm doing is we're taking 180 minus C26, which is this first angle, and then C27, which is the next angle, and it's going to give us the third degree, which is not masonry, but it's the third degree of the angle. So it's going to do this subtraction for us. Now what also is going to happen down here, we have more of the formula. So C25, so it's going to take the distance, which is C25 right here, and then it's going to take the tangent and the parallax, and it's going to give us the miles. So we're going to see that here in a little bit.
we simply minus the total degrees we observed from 180 degrees, which gives us a parallax value of 0.
Okay, 0.6. Let's get that over here. 0.6 is what he says, but it's actually 89.4. So what I'm going to do is put in
rather than 0.
89.4 here. So these are the 2 degrees we're going to play with.
0.6 degrees. And finally, we now have everything we need for our equation to solve for x. So x will represent the distance from the moon to my location in Florida. So we simply plug in the values where they belong, crunch them out, and what do you fucking know? We found that the moon is 224,573.102 miles from my front door.
Okay, so it's 224,573 miles. Okay, so let's see what we get. Let's plug in 89.4 because we had to account for Earth's curvature, and forgot that there we go. So we have to account for Earth's curvature, which gives us a parallax of 0.6, which makes this 224,573.1. Is that right? 224,573? 224,573.1. Okay, so this formula works. But what if the Earth is flat and we put in 55.4 for this degree? We go back to her original degree that she had because we say, all right, what if the Earth is flat? That's what Jainism says. Oh, wait a second. Now the moon is 3,409.143 miles away.
Which was only if you This is only if you take 2 measurements, guys.
Yeah, exactly. Take a
Need
third
3.
measurement and it won't work. As Slice Barcane showed, as Paul reminded me, as Slide demonstrated, if you take more than 2 measurements, you end up with 2 measurements, you end up with 3,000 odd miles. Immediately take a third measurement, they don't cross over, it doesn't work, it falls apart. You know it's not working, and therefore you know it's a sphere. And you just use the values of radius that you can determine in 3,000 different ways, and you end up with the right answer.
Couldn't you just do the same thing with the maths as he's just done and remove the presuppositional
I'm not
part?
saying that what you're saying is not true. I just want to see that video so I can look it over.
So yeah, if he's removing the presupposition from the maths, could you just not do that if you took 3 measurements?
If you take 3 measurements on a flat Earth, the lines don't cross on the same object. It doesn't work. Therefore, you know it's not the Earth,
TJ
it's not flat.
Chambers here with Smokescreen Design.
Maybe the Earth is wrinkled with a whole bunch of ups and downs like valleys and mountains.
For the guy that was just asking for it, I've just dropped you the link in the side chat.
No,
We live in a three-dimensional world.
Vegan's asking for a link to Slice Barcane video, I think, because it's being asserted that it doesn't work, and he wants proof of that. With 3 measurements, that is.
Sorry, Nate, you broke up then. Say that again.
So I think what Vegan's asking for is the Slice Barcane video, because there's been an assertion made that if you make 3 measurements, it doesn't line up. They don't cross.
That's right.
If you
I'm
assert that
trying
it's a
to
flat
find
plane.
that.
that is.
I think I've got it. I'm checking to make sure I do have the correct video.
I'll be honest, that's the first time I've heard that assertion made. I've not come across that one before. If you get 3 observations, it does not work. So I don't know.
Because if you just take 2, you will end up with an answer, and it just happens that's 3,000 odd miles using the Astorthisnes technique. But immediately use a third one, it's not compatible with the other 2, and you can never make them work together.
That should be the link to Slide's vid that I just posted. I think that's the one everybody's referring to.
Which one did you choose, Curve?
The world. Flat Earth Bombed.
Thank you.
Yeah.
It's about 8:58 long. It's got all the observations from.
Yep, that's the.
I'm about to check it out real quick. I'll be back.
I think Nathan should play it like you played that other one.
Yeah, it should. It's a really good one. It's a really good video.
I've got it up right now. I'm just
promise me.
going forwards to the right spot.
I've got it up. If you let me know what time marker I need to go from. It's 8 minutes long. The other one was queued up to whatever it was, 6 minutes. I just played a small section of it, but if you can tell me what part to play from, that'd be great. It's up now.
I think about 2/3 of the way through, he has all the angles, and then he goes through them on a flat.
2/3 of the way, did you say? Oh yes, I think I see. Try there. Looks about halfway.
So now, if the flat Earth claim were factual, these gray angles are what we should hope to see from all those who did the test. Let's go ahead and view the measurement results from each test.
Nathan, your stream might be able to see something, Nathan, but we don't. All right, I guess we'll have to watch the
Just while this is playing out with the measurements, does anybody in the Hangout know what specifically part of the moon they were measuring? As I said to Rumpus, he picked
If
the
you
bottom.
if you play it on the panel here, maybe we could talk about it.
Oh, is it not playing in the Hangout? Oh, I do apologise.
No.
Sorry. The audience is getting it.
And
I'll
on-
just share it with you guys. I'm really sorry.
One little thing on that point, it's the sun that they're dealing with at equinox here, right?
Yes.
But also the angular size of the sun is 1/2 degree. Anywhere you hit on the sun, you're going to be within a half a degree of each other.
Yeah, so it's insignificant in comparison to the angle they're measuring. So if someone says the angle to the sun is 33 degrees, it's going to be 0.5 out if they look at a different spot of it, and someone else is saying it's 22 degrees. It's still an insignificant error in comparison if they're looking at different bits of the sun.
And again, does anybody know the
Nathan,
setup?
if you go to around about 7 minutes.
7 minutes.
And it's not that whole center on either.
And again, does anybody know the setup of each observer? Do they have filters or anything? Do you know? I'm sorry to ask questions. So just say.
They use a stick. He asks them to use a stick and just simply look at the shadow and give. There you are. You can see at the bottom right there. He just asked them to put a stick up, make sure it was vertical, and then give the angle of the shadow as Aristophanes did. So it's obviously it's a very crude. It's quite a crude measurement, but actually it's remarkably accurate. It gives the right results for the sun. It works very well.
I have a question. Did they all do this at the exact same time?
As you can see,
when at noon, they all did it at noon for them personally.
Well, I think there goes your answer, because obviously nighttime's different for different people. If you're not doing it at the exact same time, then you're not looking at the exact same moon.
But they all did it at their own personal noon, and they then checked the angle.
Pause it right there. If you can pause it right there, what you can see is that it's a bit hard to see. The ones on the left-hand side cross in an entirely different spot than the ones on the right-hand side, and there's a couple on the right-hand side. The ones that are further out cross a lot lower down than the ones that are closer in. So there's no unique spot there that they cross over. Okay. And what he then does is he takes these measurements and he takes into account the curvature of the Earth. So if you keep on playing from here, you'll see what he does and how these results change when you take into account the curvature of the Earth.
Yeah. Whoever's complaining about the difference in time, the point is it works for a spherical Earth by doing a noon, and it doesn't work for the flat Earth.
Okay,
right.
But before we do, should we not? If you're gonna,
why doesn't it work?
If we're going to add in curvature measurements, what is this shot now?
Why specifically is it impossible on a flat plane that makes it completely possible on a spinning ball?
Well, it's the fact that the observations are taken from a three-dimensional object, and when you plot it on a two-dimensional plane, it doesn't line up. That is the point.
But should we not see a curve that they start from? You see all these lines on the bottom. We've got this line that runs across. Should we not?
This is his assuming that it's on a flat plane. So this is from the standpoint of the assumption that it's on a flat plane, and you can see that the lines don't cross in a unique point.
Yeah, but hang on. You can also see that, but for one of them, they were all pretty close.
No, they're not.
They're not.
And refraction would account for that easily.
No.
It looks like a lot of the lines coming from the right side meet and intersect at a much different point than where the sun is.
Yes, that's correct.
And the point is, when you use the spherical model, everything lines up. You don't need to take anything into account. It all works on the spherical model. They all cross over at the right point within the acceptable margin of error. Whereas if you use the flat Earth model, it doesn't. And you can't bend refracting. Refracting it's not going to fix it, but you don't need to, because on the spherical model, it all works.
Yeah, and refraction is not considered, right?
Yeah, but it all works. But refraction is. Remember that they're all looking high. Remember, they're all looking high up at noon. Refraction doesn't. If you look at the Mick West videos, he demonstrates how refraction. And if for instance, all these refraction effects that we see with Fata Morganas and things, and when you look, for instance, along Lake Chicago and see buildings inverted or whatever, they all occur when you're looking at very low angles. These people are looking at very high up, and this is why astronomers, they never do any observations on things below about 20 to 30 degrees. They all like to look straight up into the sky, and these observations were done at noon, where the sun is at its highest. So all these observations where refraction is almost insignificant. So that's why refraction isn't an issue.
Hold on, sorry. Hold on a second.
And that's demonstrated by the fact that it all works for the global Earth model.
I didn't see
Why is all of the globe proof evidence in digital modeling and not in reality?
Sorry, I've just got one question again. Sorry, just to round this out, guys. I just want to ask a question about the Slice Parkane video. I'll turn it down because I want to ask a question which is more important. So, right, so I didn't actually see it modelled. I mean,
Why can't we see this stuff observable reality?
You can. You just did.
Watch a boat go below the horizon.
I need to ask a quick question. Can I ask you, Rumpus? Because it was you that suggested this video, I think, maybe.
Yeah.
Either way.
It's actually Paul, but I completely agree with the suggestion. It's a fantastic video.
Okay, so we don't actually see it modelled, because obviously if you push the moon much further away, the margin for error would change radically, wouldn't it?
Well, hold on. He puts all the observations. He assumes a flat Earth, and then he sees that all the observations do not cross on the same point. In other words, all these people apparently are looking at different
I'll address
things.
Paul. Sorry, Paul. You've said that it was modelled out so that we could see it on the Earth. Obviously, we'd have to have in scale on this. To get it to scale on this page, the moon would be a tiny little dot on the left side, and
these are observations to the sun, not the moon.
Sorry, the sun then. Either way, well, that would make it even worse. Would that not put the margin of error massively in the favour of making it seem spherical?
No, there's no margin of error here. What people did was
by scaling it up. What I'm saying is by pushing the distance of the sun further away.
At noon. Okay.
I haven't finished. So if you push the sun much further out, because what we have in the picture at the end, as opposed to the depiction of the flat Earth model, let's bring that back up. Where is it? Here we go. So we actually have the sun and all of the lines from the ground to the sun, but we don't have the same depiction, which would obviously in scale push the sun massively. We've got this massive great big Earth and then just lines coming from it. We don't actually have it shown.
Well, that's because it's far away. It's on the scale of the Earth. The sun is so much further away. That's the point of a flat Earth model.
But your model shows
the whole point. That's the whole point of this demonstration. Is that
the sun is a long way away.
Yeah, the sun is a long way away.
In your model,
it doesn't show it modelled. It doesn't show them all converging on the sun. Where's that in this video?
Let it roll.
It shows that the sun rays are almost parallel when we see them at the Earth. That's what this demonstrates. And that indicates that the sun is a long way away.
It doesn't show it modelled.
The center of our big round Earth.
I don't see it modelled anywhere. It doesn't
get
hold on.
Nathan, you can't. When you show the Earth at that scale, you can't show the sun as well.
Of course you can. You just make the Earth very small. So you tell me where it shows it modelled.
Those who seem to be seeking the truth.
The parallel lines.
Want to participate in finding it.
No, I want to see the sun and the Earth in the same shot. Is that unreasonable? That's what we're demonstrating, and we don't see it.
It is unreasonable.
Okay,
if you were to,
I can demonstrate. I can actually do this for you, actually, Nathan. I've actually got a diagram here of them in the same shot. I can show you what
that would make me much happier. Thank you, Olympus. Yes, please.
Right, I will just demonstrate to you. So I'll screen share and show you what it's actually like. Let me go. Let me screen share this. I've got a little diagram that demonstrates this thing exactly. Here we go. Let me just go to 5%. I think it's 5% I have to do. Right, here is a scale view of the solar system. Can you see that?
Yeah.
Oh, great. So here we have the sun, and all of this is to scale. Everything in this is to scale. So there's the sun.
Where's the lines? Where's the lines of the observations made on this model?
Well, I'm just hold on. I just want to demonstrate what the scale of the sun.
So you appreciate
the
scale model of the universe.
They don't understand the scale.
No, I do understand scale, Rumpus. You don't need to patronise me. I understand the scale of the sun and the Earth.
Let me show you how small the Earth is, and that's what.
This is not what I asked for.
Why didn't you show the sun?
Rumpus, this isn't what I asked for. Rumpus, I asked for that experiment shown on a model, not a scale model of the universe. I've seen it.
Why he couldn't show the Earth and the sun in the same picture as he could in the flat Earth
just
model.
Had some
you can't model reality.
Hold on, Truth. Rumpus, let me address this.
I'm about to show you how you can do it. So here I have the sun. There's Mercury, Venus, and the Earth, and that's that little blob in the right-hand side. Let's see how far we have to zoom in to show the Earth.
Rumpus, so he just had a model of the Earth.
Here we go. So there we go. Oh, that's still not the Earth. That's my expansion. If we go in again, there it is.
Rumpus.
Oh, look, that little blob there is the Earth.
I understand.
And I've now had to zoom in 39,000% to show you. And so if they wanted to draw the sun in that Slice Barkane's video, it's all the way over here.
Yeah, he could have easily modelled it.
So he can't show you. So
yes, he can. This is nonsense. No, we can't show you is a nonsense answer. Yes, he had a piece of model that showed the beginning of it, and it started to zoom out, but we never actually saw it.
Nathan,
we could have easily
how stupid are you?
Excuse me. We could have easily
seen.
Hold on. we could have easily seen what you have there with you zooming across. You could do it live now if you had those lines drawn. You just don't have them. So how the hell do we know that it shows that?
You couldn't even see those lines, okay?
We can zoom. We have the
scale.
technology, Louis. We can zoom. We can show it. We can drag the lines across. I've seen Jaron do examples of exactly
it's hilarious.
that.
Like you, on one hand, you have Nathan saying we want a better virtual model, and on the other hand, you have Truth saying it's a virtual model, so it's no good.
Well, no. It's not. It's a model of something we've taken measurements for, and the assertion is that they perfectly cross on the sun from the Earth on the spherical model, and they don't from the flat Earth model. But we don't get to see it being modelled on the spherical model because apparently it's just too big to show.
Well,
what a
Nathan,
load of nonsense!
how else would the
we have
light
the technology.
come in
We have
but
zoom.
Parallel?
We can
Nathan,
zoom.
Parallel.
Nathan, just imagine.
So parallel.
Imagine that the sun is as massive as it appears to be in this scale compared to the Earth. How would the light be coming in
as I
any
said at
other
the beginning,
way?
Louis, that would put the margin of error massively in your favour, would it not?
It would only come in parallel.
It would put the margin of error massively in your favour by pushing those distances that far, which is the first thing I said.
It also matches up with the measurements that we made. So.
Excuse me, I've said it 3 times. It pushes the margin of error in your favour, and we don't get to see it modelled.
Well, I mean, ignoring trigonometry and everything that we've shown you here today,
anything.
or
You
I'm
haven't
sorry,
shown
that
anything.
Rumpus,
You haven't
Paul,
shown it. You have not shown it. You haven't shown it.
Right, sure. I understand. I haven't shown you, but I did initially tell you that trigonometry was the answer. Now, that's not doing a whole lot of work, but everything that's been shown to you here today is a very long-winded, detailed trigonometry lesson.
Yeah.
Can I ask Rumpus a question?
Yeah, please do.
Nathan, would you share my screen, please, mate?
Yep, you're sharing.
I was like, okay, so the assertion was that all the rays from the sun are parallel. If that's the case, how is it possible that we get hotspots on the surface of the Earth when the Earth is receiving parallel light and all the light should be evenly distributed across the side of the...
No, it shouldn't, because it comes at an angle. Let me show you. I can demonstrate that to you straight away.
They're not hotspots. They're specular reflections.
And it's the same. It's the same way that
they change.
It's the same way that hot spots appear on vehicles when you're driving down the road, and that bit of glare on the windshield or along the edge of the car. It's the same. It's literally the same as that.
It's a specular highlight.
Yep.
So you're.
I saw a hot spot on D Marble's head.
Right.
Yes.
Exactly. It's the same as that.
I'm not quite sure. What?
By the way, in case you're wondering, it's because apparently it bounces off the sea and then reflects.
Exactly. Yes, I must admit, this is something I didn't spot initially. Those hot spots that people thought was a bit confused by them. When it turns out, Slice Barcane did a fantastic job of showing that exactly where the hot spots were, exactly where bodies of water were. And before that, in other hangouts elsewhere, I'd seen with advice of people like Cara had shown me that all the hot spots that people see and say, oh, it looks as if it's on the clouds, it's actually light reflected off bodies of water underneath the clouds. And what's it you just said? Slice Barcane actually shows it with a picture from a satellite, from a balloon that's looking at a hotspot, and then he shows where it is on Google Maps. He then shows the location to where the hotspot's coming from, and the shape of the hotspot exactly matches a body of water underneath the clouds.
Sure, but the fact that there's a hotspot there is the issue.
It's just a reflection in
No,
water.
it's not an issue at all.
It's just a reflection in water.
How can there be a hotspot if all the light rays that hit the Earth are parallel?
Because when light is reflected off the water, that creates a hotspot. You see, it's because of the water, not because of the angle of the rays.
And
it's
because also
of what the light is hitting. It's
but
like
it's
how
It's a function of the observer as well. So if you move around, that hotspot is going to appear to change location, and that's not because the focus of the light's changing. It's because that hotspot is a function of how our eyes work.
But all the lights hitting the Earth parallel.
let's say
light bulb in a.
That's right. Have you noticed that these reflections, these specular reflections, are always in line between the observer and the sun? How come you don't ever see them out of line? It's because reflections work in a plane. The light bounces off the surface and comes towards you.
But the
Don't
point is,
hit
all
the fever.
the lights,
You don't
all
ever
the
see
light
him
rays
to
are
the
coming
left or
in.
to the right.
Sleeping,
Okay.
If all the light rays are coming in
something-
parallel, there cannot be a hotspot. That
Sleeping.
indicates
Here's something you can do.
close.
Absolutely.
Sleeping. Here's something you can do for yourself. Take a magnifying glass and then put it over, focus it over a sheet of glass, and I don't know, what's something that conducts heat really well, or does I don't know, some good conductor like copper or something that conducts heat well. Then put it over for the same amount of time. Touch that spot. One of them is going to be warmer than the other. That's because it's the surface that changes, not the amount of light, not the direction of the light. It's just the surface.
I mean, I don't think that really helps very much. Take a flashlight and shine it at something, and you'll find that there's a hot spot on that. And as you move around,
correct,
and change your location in the room, your eyes will perceive a change in where that hot spot is on the
Yeah, the
object
problem is the hot
that
spot's
light is
close.
shining onto.
The
Anthony.
light's close, though, isn't it? That in that
Doesn't
instance.
matter. Doesn't matter. It's the
Doesn't have to be.
parallelness. It's the parallelness, Anthony.
All right. Well,
which
if you guys
be
don't
your
accept that
contention
point, then
here.
let's move on.
Oh yeah, let's
and
move on.
just a quick point. Just a quick
Schooled
point.
you on
Anthony.
everything here. Come on.
Anthony, have you not seen reflections off a body of water? I mean, if you go on a canal holiday, on a river holiday or something, have you not been a case where you've seen smooth water and you can see objects which are have distant objects like the sun coming in or other distant objects, and they reflect perfectly off the flat water, and it's just a function of angle of incidence equals angle of reflection. I mean, it's very, very easy. I don't understand your problem at all.
Very easy. But the problem
I
is,
have a question too.
it is very easy. I agree, but when you model the light coming in from the sun on a sphere, the
What's
light is
very
always
easy, Anthony? What's
the
very
light
easy?
is-
I'd like you to hear.
Lewis.
I'd like to hear your words on what is very easy, because I think you just like to agree with people to kind of skedaddle out of answering that specific thing.
When you model a distant light source on a sphere, the light is always on the horizon. It's never in the middle ground or the foreground like we see reflections from the sun. It's always on the horizon.
Yes, it is.
That's nonsense.
That's that's an absurd statement, Anthony.
I can
It
prove
is.
it.
That's an absurd statement.
Bear with me and I'll prove it.
No, I'm not going to bear with you on that. I have my better reasoning.
Well, let's see him prove it, because if we don't let him try to prove it, then he's just gonna say, "Well, you're scared of us proving you wrong."
Well, let him say that then, Joseph.
I'm going to let you all into a little secret, by the way. Light from the sun is not quite parallel, because if it were, then you wouldn't be able to see the top and bottom of the sun. The fact that it is actually a 0.5 degree difference between the top and the bottom, so the actual rays actually do come at you at a slightly different angles from one side of the sun than the other. So for instance, a light coming from here, I don't know if I'm still presenting to you, a light coming from here, that actually is a naught. So if someone here is looking at the, let me just move that again. This thing here, whoops, bloody hell.
Right, but the scale of the Earth compared to the size of the
that is only
sun.
that angle there is 0.5. Oops. That angle there is 0.5 degrees, and so in fact the light is not quite parallel, because obviously the sun has size. It has an angular size, and that angular size is 0.5 degrees.
Right.
And so therefore it's not quite parallel. It's very close to parallel, but actually there is a slight angle difference from the top and the bottom. That's why it has an angular diameter. If it was a point source, then it would be parallel. So for instance, a distant star, that would be parallel, but the sun is sufficiently close that in fact it's nearly parallel, but not quite.
So how can a convex light create converging light rays?
What?
How can a convex light source?
You're going to ask about.
converging-
You're going to say how's an eclipse work, aren't you? Is that what you're going to say?
Well, yeah, we see, because to my knowledge, I thought that light is perpendicular to the surface. So if you have a convex light source, then the light ray should be convex, not converging. So
They're
not converging.
The light is radiating out in all directions, right? This convergence is simply the angle that an observer would notice when he looks at the top of the sun versus the bottom.
No, but
no.
See, is it a fact that light shines perpendicular to its surface?
Depends
no,
on
that's what confused. I can explain to you. Here, I can explain the answer to that exact immediately. The light from the sun comes out of here, goes there, goes here. So no, it doesn't come out perpendicular. So it goes out in every single direction you can possibly imagine. It goes out in 360 degrees. And obviously, if it goes back into the sun, you don't see it. So it comes out in every single direction from the sun. But obviously, the only bits you're going to see, obviously, the bits that are coming towards you.
Hey, Rumpus, for this deviation from parallel, is it worthwhile or is it correct to consider the angular size of the Earth from the viewpoint of the sun?
Give me that again, curved.
To determine like the deviation from parallel.
Yeah, which is 0.5 degrees. Yeah.
No, the sun is
that's not right.
25 degrees.
Sorry, I didn't.
The angular size of the Earth, as seen from the sun, isn't that going to give you some kind of an idea of how far from parallel the rays can be maximum or not?
Well,
yes, it will.
So I'm missing people over talking about like it and didn't. The angular size of the sun is the same size as the moon, and that is 0.5 degrees.
Right.
That's from the point of view of the Earth, though.
Yes, correct.
Curve was asking.
You need to look at it from the other end.
Right.
Okay.
Curve,
the light rays are diverging from the sun, and what we're looking at is the angular size of the Earth as seen from the sun.
Right. Okay.
The divergence. Yeah.
Right. So we're looking. So here we are. So if you were an observer on the sun, so if you were sitting on the sun here, and you were there, you would see the Earth as being. Let's get rid of this crap.
Well, that might be underfiguring it. Now that I think about it again.
So the question is, is the question, how big does the Earth appear in what's the angular size of the Earth from the sun? Is that what you're saying?
Well, no, I'm thinking about the maximum from parallel. Like, sun from one side, light from one side of the sun versus the other side crossing at the Earth. Like, what's the maximum deviation from parallel for those?
Because obviously the Earth, that would be much less than 0.5 degrees. So in other words, the light from the Earth to the sun is going to be much more parallel than the light from the sun to the Earth, because obviously the sun's so much bigger. I'm still not quite understanding the question, I'm afraid.
Okay, I have another question.
I'm trying to get a handle on how far from parallel.
I have a question.
Well, it's 0.5. Well, it's 0.0. Well, it's not as far if. Well, it's
no,
that's
from the point of view of the Earth.
Yes, so in other words, the light. So right, so okay, so
I've just calculated it curved. It's 17 and a half arc seconds. It's not much at all.
Very good, thanks.
Okay. So can I ask my question now?
Yeah.
So let's say we have a sunspot on the Earth, right?
Sunspot. Hold on, a sunspot on the Earth. I don't understand that concept.
Or a hotspot on the Earth. I'm sorry, a hotspot on the Earth. Right.
So reflection. So it hits. So some light from the sun hits some body of water and reflects off it. Right. Yes.
Wouldn't the hotspot show how fast the Earth is moving?
How fast?
What?
Because think about it. So listen. So the hotspot isn't moving, right? Would it be moving with the Earth?
It's just hotspot is nothing more than reflection of body of water. The body of water is moving with the Earth.
So okay, let's say you have
that
a lamp
hot
in your room.
spot could be used to determine where the observer is. That's what it could.
My point.
And it could also. I'm answering your point. It could also be used to determine the motion. I do understand. It could be used to determine the motion of the observer relative to the Earth as well.
Okay, so let's say you have a lamp, right? And you put a Sprite bottle in front of your lamp, okay? And then you start spinning your Sprite bottle 100 miles per hour. You can see that the letters on your Sprite bottle are moving relative to that stationary hotspot. So
and we have tools that can do this. We have tools that use laser beams that measure the revolutions per minute of various objects and various spinning things. Here, that's a tool.
Well, my point is that on the hotspot, shouldn't we see the clouds move thousands of miles per hour relative to the hotspot?
No.
Why not?
0.005 RPMs.
Because the observer is going to be contrary to your example, right? The spinning object with your lamp is
No, my lamp
is moving in a different reference frame from the light source. Whereas
Right,
the and you
more
and
to the
also
point, more
and
to the
also
point
use
is
the observer.
more to the point is that the rate of spin is so slow, you'd have to observe it for literally half a day or hours to see that rotation.
And
but relative to the hotspot, it'll be pretty fast because the hotspot stands still. So basically, if you
right,
have
but where are you?
hold on.
It's about the
revolution
observer,
per
vegan.
day.
It's about the observer, vegan.
So if you have something
One
standing
revolution per day, vegan. One revolution. Try spinning your Coke bottle at 1 revolution per day.
All right,
and see
okay.
how much you
It's
can
the
see
hour
the
hand going
let it
around.
spin.
But okay, but the reason you should be able to see it is because if say I'm standing by a car that's going 1,000 miles per hour, okay. If an observer
Stop
looked
1,000
at
miles per hour business. 1 revolution per day.
Okay. Is the Earth spinning at 1,000 miles per hour? Yes or no?
No, it's spinning at 1 revolution per day. We don't measure spin in miles per hour.
Yeah, at the poles it's 0. At the equator it's 1,000 miles an hour, but the poles it's 0.
Oh my gosh. Okay, so you're telling me that the Earth is okay. Whatever you want to say, how fast the Earth is spinning. It's spinning pretty fast, correct?
No, it's spinning at 1 revolution per 24 hours.
Think about it, dude.
At the poles, it's 0. So here, you're moving at 0 miles per hour, and here, you're moving at 1,000 miles per hour. If I'm still screening, if people can still see this. So there,
Yeah, so it has an edge velocity of 1,000 miles an hour. That's pretty fast.
Yes. So relative to the hot spot, you should see it moving at 1,000 miles per hour because the hot spot is standing still.
You are on the Earth too.
Then we should see the hot spot. Then we should be going away from the hot spot at 1,000 miles per hour.
But dude,
I mean, let me just remind you,
there's a huge variable missing.
1,000 miles per hour on the scale of the Earth is a rotation of 15 degrees per hour. You will have to wait an hour to see that ball rotate 15 degrees.
Yeah. If you were to watch this, I mean, if
but
this was
relative to the hot spot, it would still be obvious because the hot spot is not moving at all.
If you wait an hour, you will see it move, but you don't see balloon footage taking videos of a length of an hour focusing on the one hotspot ever, do you?
Okay, how big do you think the hotspot
until
is?
you can get a video of a so-called hotspot from the same position in space, in other words, the observer is not moving relative to the Earth, okay, then you need to observe that hotspot for a period of time of well over an hour to see any noticeable movement.
Well, see, the thing is, though, even if it's moving only fractions of a degree, like you said 15 degrees or whatever, that's still thousands of miles. Is that not correct?
But
That's right. But you're not going to see that because it's only rotating 15 degrees. Try. Can you see the hour hand on your clock move? Because it spins twice as fast as the rotation of the Earth. Try looking at your analog clock and wait. How long do you have to wait before you notice that the hour hand moves part-time?
Imagine this was a video. Imagine
You're talking
if I'm
across
still screen sharing.
purposes,
Imagine this Earth
Oops.
that I'm looking at is a video of it.
Hold on, who's screen sharing?
If I'm still screen sharing, if you imagine the Earth that I've got here is a video and not just a still.
Okay.
That would look just like the video. That picture there would be doing nothing. And after 15 minutes, the Australia would have moved very slightly to the left. After,
Rumpus, sorry to interrupt you, Rumpus.
So after an hour, it would have moved 15 degrees.
I think the problem is that Paul and Part-Time Vegan are talking at cross purposes. So Part-Time Vegan's talking about edge velocity and Paul is talking about rotation speed. One seems very slow, one is very fast, and you've defined it. You've got it here, 1,000 miles per hour. You've got it written down.
But it's relative.
How many of those 1,000 miles would you need for it to go halfway around the Earth, though?
Yes, well, you're now changing
You'd need
something very
20
fast into something
hours,
very slow by
wouldn't you?
making that statement, which is clever, but
Wait,
still.
wait.
Okay. He's asking us how we could determine the speed of the distance of the specular highlight or the hotspot. saying.
But what's this
That's
obsession
what he's
with
saying, is that it
hotspots?
doesn't appear to be moving that fast. So it take a very long time to see the distance.
Why not just focus on a feature on the Earth? Why worry about hotspots? Just
Because the
simply-
hotspot doesn't move. Because if you're moving with the Earth, of course it's going to appear like the object is moving with you. But the hotspot would
Part-time vegan, if you're moving with the Earth, the hotspot is also not going to move. It blows my mind that you can't grasp this. If you move relative to your reflection in the mirror, it moves in your perception of it as well. If you stay still, it is not going to move. If you put yourself on a merry-go-round with a mirror and you look at that shit, excuse me, sorry for swearing, that your reflection isn't going to move on that
I
merry-go-round.
think the reflection is a good analogy. So let's say I'm looking at my reflection in the mirror, right? And this mirror is pretty big, and there's a smudge in my mirror, right? I should see that if my mirror is moving 1,000 miles per hour, then I should see that smudge go across my reflection at 1,000 miles per hour.
Not if you are also moving at 1,000 miles per hour.
Okay,
imagine if you're on a train, for instance, and you're going along at 200 miles an hour on a train, everything moves along you with the train. You can play a game of tennis in there, or you can throw balls up in the air and they come back and land in your lap.
Okay, so we have approximately half an hour left on this live stream. Thank you, huge thanks to all the people who have shared this show, as there's been quite a huge number of people, 150 people watching in the live stream, so massive thanks to all who shared the show. If you are new to this channel, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth debate. If you would like to support this channel, or you've been enjoying these live streams, toss me a buck or two in the super chat, which runs alongside the show while it is live. And if you would like to join the debate, there is a link in the info box below this video. With the page you are currently watching on mute, simply click that link to join the show and express your views on the shape of the Earth. There are a couple of rules in the Hangout. Number 1, please do not swear. If you do, you will be ejected. And if you are, please do not try to rejoin the stream using sock accounts. You will be warmly welcome back on the next show. Now, we currently have a full house of about 10 people on the panel, so you may have to wait till somebody drops, or there is a network area if you want to sneak on the show. But as I say, there is about half an hour left. One more time, if you're new to the channel or you've not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth debate.
But because the sun is so far away, even though we're moving 64,000 miles an hour, it doesn't appear to move very quickly. And obviously the rotation of the Earth also adds to that. But both issues mean that the sun, you're not going to move, because the sun is so far away, you're looking at a line to the sun. That line is not going to move very quickly because the sun is so far away.
So let's say,
For instance,
the hotspot is over.
If you're looking at a hill in the distance and you move left and right, you will see that the hill doesn't move very much. Whereas if you've got a tree in front of you and you move left and right, the tree will appear to move very rapidly. But if you're looking at a hill, you will see almost no movement as you move left and right. The same is true when you're looking at a hotspot, as you call it, which is nothing more than a line to the sun. The sun is not going to move very much, even if you move at 1,000 miles an hour or 64,000 miles an hour in orbit.
So when you say that, so you mean, okay, so we see the hotspot based on the reflection of the sun. Is that correct?
Yes. And where you are
we agree
and
on
your
that.
motion relative to the thing being reflected off.
So what I'm saying is, if we're seeing the sun, like you said, the sun isn't moving, the Earth is moving, all right, and we're moving with the Earth. So even though we're moving with the Earth, we should see the hotspot moving at 1,000 miles per hour, because that hotspot is just a
But you might as well
reflection.
say, but hold on, you might as well say we see the sun move at 1,000 miles an hour. If your argument is correct, then the sun would be seen to be moving at 1,000 miles an hour, but it isn't because it's so far away.
No. Can I explain it, please, to part-time? Part-time's right. The hotspot would move at 1,000 miles per hour. But what part-time doesn't seem to be understanding is that 1,000 miles is a distance of, it happens over a time period of an hour. And that 1,000 miles is a very small fraction of the circumference of the Earth.
Of the orbit.
Think about that 1,000 miles in reference to the 40,000 miles distance around the Earth. It's not much of that distance.
Exactly.
And so to see, remember also, to see that change, you're going to have to wait for an hour.
Yeah,
so you are going to have to
Sorry,
wait
Rumpus,
for an
can you
hour
stop screen sharing?
to see.
Just stop it.
You're going to have to wait for an hour to see a difference of 1,000 miles, which is a very small portion of the circumference of the Earth. And so it's not going to appear to move that far over the whole circumference of the Earth. And you're going to have to wait an hour for that to happen.
Can you stop screen sharing, Rumpus? It's just it gives the audience
I've got
epilepsy.
one important thing to show to demonstrate this scale thing. Imagine, in fact, this will answer his question. You see this scale here? I've forgotten who's got the problem here. If this little dot here, remember, this is 93 million miles, and here's the Earth here, and it moves in its orbit by 1,000 miles an hour. That's less than a pixel on my screen here, much less than a pixel. Can you see that it will not make any difference to the light from the sun to the Earth? It will make no difference. Even though this Earth is moving 1,000 miles an hour, the angle, which is effectively what you pick up on, will not change at all, just about. So
let's say I'm looking at it. Okay. So we agree. Me and Paul agree that I would see it move at 1,000 miles per hour. But the thing is, it's such a minuscule.
No.
Can you just let him talk, please? Can you just let him talk? I want to hear what he has to say.
See, this is what happens. We got three people saying three different things. But Paul, okay, you see where I'm coming from. Okay, so yes,
I want to hear
you're
what you have to
correct
say.
that. Okay, so we agree that the sun, we should see the hot spot moving at 1,000 miles per hour. But you're saying that is such a small, or not such a small distance, but it will take an hour, so you will hardly see anything. Is that correct?
That's correct. Yes.
So
because the change in angle is what you're looking out for. You are going to notice it by a change in angle of the position of the sun. But the angle will not change at all because it's
I just did the math, and it said that it would be moving at basically 0.2 miles per second. I think I would notice an object moving at 0.2.
Okay, can I just okay. So, part-time vegan. Not only is the hotspot moving at 0.2 miles a second yeah. So are you.
No.
Yeah, yes.
You don't get it, man.
No, you don't get it.
Yeah, okay. So what the hotspot is, right? It's the water underneath the clouds. So the water is part of the Earth. Therefore, the water moves with the Earth. And since it's moving with the Earth at that 0.2 miles a second, and so are you, to you, it seems like it's staying in the same place. But if you were, let's say, in orbit, you would be able to see it over an hour change 15 degrees.
And you are also changing when you're in orbit, and so you would see that hotspot change.
Whether I'm moving with the object or against the object.
That is entirely relevant because you, the hotspot, and the light source create a triangle. And when you and the hotspot are moving at the same rate on the Earth, the changing variable is the sun.
Part-time. Can I explain it to you trying to use a diagram here?
Guys,
Can you see my
Nathan
screen?
wants us to stop.
Hold on. Let me look at Paul because you guys don't know what you're talking about.
Nathan wants us to stop screen sharing so much.
It's just if you're not actually presenting something. So Paul's fine to hold on, Paul. Hold on, Paul.
All right,
Sorry,
Paul.
Paul. Hold on. So if you finish presenting Rumpus and Sleeping Warrior, can you just stop screen sharing? Thanks. Thanks. It's just once you talk, it gives flashes.
Yep. Okay. Can you see what I've got on my screen part-time?
Yes.
Okay. This circle represents the Earth, right?
Right.
This represents one single ray of light coming from the sun. There are obviously more coming from the sun. Okay. Given that the sun's a long way away, a ray of light's going to come in from the sun. It really doesn't matter whether it's close or far away. We've got a ray of light from the sun coming in, and it bounces off the Earth and goes over here. And this is where our observer is. So I'm just going to draw something over here. I don't know. I'm going to have to use the pen to do that, aren't I? Okay. So here's my observer. Okay.
Right.
There's my observer. We see that ray reflected. So we perceive there to be a hot spot on the Earth here because that's where we're seeing the reflected. Do you understand that?
Right.
Cool. Okay. This here represents the radius of the Earth to that point.
Big shout out to Joss for his super chat. Thank you very much.
You can see that. Okay. Now, how far is the Earth going to rotate in 1 hour? In 1 hour, okay, we all know the positions of the clock. That's about 1 o'clock. That's about 2 o'clock. That's about 3 o'clock. Would you agree with that?
Right. Yeah.
Okay. So remember, the Earth spins one rotation in 24 hours. The hour hand of a clock spins one rotation in 12 hours. So we're expecting the Earth to rotate half the distance between the 1 o'clock position and the 12 o'clock position. So that's about there in 1 hour. So we're expecting our hotspot to then be there. So if the Earth's rotating this way, okay, we're expecting that hotspot to be there because it will have moved into that position at that time. Do you agree with that?
Right. Yeah, I agree with that.
Okay. So have a look. All right. We have seen those hotspots aren't very far apart considering the total size around the whole Earth. And we have to wait for an hour for it to move that far. It's not whizzing around as fast as you perceive it to be. 1,000 miles an hour when you have to go 25,000 miles is not a very fast speed.
Because you work in angles.
Okay, hold on. Let me talk to Paul. So, do you still agree that that's still moving at 0.2 miles per second?
Oh my God.
That's right.
So let me ask you this.
Talking about so big, you're not going to witness that speed.
Okay, so
because you're looking at a huge distance.
Let me ask you this, Paul. Let me ask you this real quick. Okay, so let's say we have a small ball, all right? And this ball is moving, and you're looking at the ball from your perspective. And the ball is, let's say it's a basketball. It has Spalding on it, okay? You're looking at the word Spalding, and that ball is rotating at 0.2 miles per second.
No, that's
is that fast or is that slow or like what would that look like?
You're now spinning that ball much faster to achieve that speed. You need to spin the ball at 1 rotation per 24 hours.
So you're basically saying that if that ball was to just grow to the Earth size, it wouldn't seem like it was going that fast.
That more
to me,
the
that's
point
kind of
is
hard to conceptualize.
if you shrink the size of basketball, how fast would the edge of it be going?
If you okay, well, my thing is you're saying that if you have two objects, one's an Earth and one's a basketball, and they're both spinning at 0.2 miles per second, you're saying on one object we can see it's going fast, and the other object we can't see it's going fast, and I don't understand why not.
The reason why part-time is because to achieve that speed of 0.2 miles per second on the basketball, you would have to spin the absolute bejeebers out of it. It would not be spinning at 1 revolution per 24 hours. If you spun the basketball at 1 revolution per 24 hours, the speed would not be 0.2 miles per second. It would be a fraction of a millimeter per second.
Check this
You're
out.
not going to see that.
Part-time vegan. You know how when you stand on a merry-go-round or whatever, and everyone walks towards the center and it speeds up, and then everyone goes to the outsides and it slows down. The speed that you are physically moving, or let's take a simpler example. You're spinning on a chair and you bring your arms in and you speed up. You right here on your body are actually spinning, even though it's more rotations, you're spinning at virtually the same speed that the tips of your fingers are, even though it's less rotations that the tips of your fingers are when you put your arms out.
To me, I would feel that regardless of the size of the ball, we would be able to distinguish what's 0.2 miles per second. But I'll look into it. I understand what you're saying, Paul.
The point I'm trying to make part-time is that if you shrink the Earth down to the size of a basketball and rotate it at the same rate as the Earth, the edge of the basketball is not going to be moving at 0.2 miles per second. It's only going to be moving at a fraction of a millimeter per second, if that. And you're saying you can see that?
I'm saying if we so is it angular velocity?
That's correct. Now we're starting to get there.
Okay, so so if a small ball and a big ball have the same angular velocity,
yes,
of 1,000 miles per hour.
No.
You're saying that
No, an angular velocity is not measured in miles per hour. It's measured in degrees per second or degrees per hour or revolutions per minute or revolutions per day in the sense of the Earth.
Sorry to interrupt, guys.
You
just
get
want to say a quick.
man?
Sorry to interrupt, Paul. We just want to say a quick hello to Grim and can say if you've done screen sharing, can you just stop just so it doesn't keep flashing every time you talk. Hi, Grim. How you doing?
Hey, buddy.
Good to have you
Revolutions
here.
per day. Let's do it.
Good to see you.
You too, Nathan.
Revolution.
Yeah. So you understand part-time, but it's not miles per hour. It's revolutions per time period. Revolutions per day in the sense of the Earth. So you have to spin the basketball at 1 revolution per day to make your experiment comparable to the Earth.
Can I try to give this to him in a visual form that he should be able to understand?
Have a go.
Just take a second. All right, part-time. Anthony's gone, but did you see the image that he had up on his screen there for a while? You got somebody out there on the water. They're looking at that reflection from the sun that runs from them to the sun. Did you see that?
Right.
Okay. Now imagine you're there with that camera and you're filming the reflection. Okay.
Right.
Now, the reflection is going to move at the rate that the sun moves left to right in your vision there, because I'm assuming we're looking southward at the sun because I'm a northern hemisphere guy. So we're assuming the sun is moving left to right. That reflection is going to move. You're going to have to rotate your body at the rate that the sun is moving in azimuth across the sky. You know how slowly that moves. That's what you have to do to track with that reflection. Do you get that?
Oh boy.
Yeah. Took more to
So
visualize it, but yeah.
how many thousands of miles an hour do we have to run to keep up with the reflection? We just have to rotate our body very, very slowly and rotate the camera to track with the sun, and you're going to be tracking with that reflection. Correct?
I got you.
Thank you.
So there we won, didn't we? Flat Earth finally finished. Right?
Well, don't jump the gun here. Here comes Nathan. Like, wait, hold on now.
Way back onto Skype. But that was a good. That was good. That was a good.
Yeah, no, that was a good one.
It was really
Yeah.
good.
I was gonna do things about relative size and stuff, but no, that was a lot better.
Yeah, I was impressed. That was great.
Wait, is it over? Did I miss everything? No.
Yes.
I'm
We're done.
joking. That was
Sure
good.
effort.
That was
Goodbye.
Good. We can cuss now?
No.
Oh, never mind. Okay.
So is Anthony going to come on Skype and do his thing?
Yeah,
No, I
did he
can't get hold of him. I've tried. He's
did he
been sniped
crash or
out.
something?
He's been sniped out
He
the
probably
hangout,
felt
but
when I jumped in, like, whomp.
yeah, he's been sniped out the hangout for some reason. I don't know why he hadn't said anything for ages.
I've got an. Is part-time still in?
Yeah.
Yeah, I'm still in.
So
Yeah.
tell him
Okay.
to keep trying to get in.
I've got an interesting video for you, part-time. All right. You don't have to hear it or listen to it, but can you see what's on my screen there now?
Yeah.
Okay. This is a video. I'm going to play it. Right. This is the Earth rotating at real-time speed. Very exciting, isn't it? Can you see it whizzing around at 1,000 miles an hour?
Yeah, this is the point I was making earlier about my graphic about the Earth. It's effectively a video. That's exactly what it would look like as a video. It's stationary.
This is the real-time rotation of the Earth.
He's sharing a
So
mouse.
fast, isn't it?
I mean, I
Is
don't
this
quite.
taken from a satellite, I presume?
Yes, that is taken from a satellite.
How far is that satellite? Does it say?
It's taken from the.
That's quite a long way away. That's
Galileo.
From the Galileo satellite.
Looks
Yeah.
stationary.
Look it up.
On the hangout,
Okay.
you're just seeing transformers and mouths and stuff.
I mean, part-time.
Does it not tell the exact distance it is away from Earth though? It doesn't say that.
Well,
I don't know, but the point is that you can't detect the rotation there by looking at it for a few minutes, could you?
No.
Okay.
I mean, I don't quite understand part-time. When you look at an aeroplane, you know it's doing 500 miles an hour and it's in the distance. You can't see it move. That's a very similar situation. So I don't quite understand your problem at all. things that are a long way away don't move very quickly.
And to talk about like your thing of how 1,000 miles is really fast. It is really fast if you're on the scale of a human. But to compare, let's say you are an ant, right? Or a snail, because whatever. An ant, because they're smaller. If a human is jogging past you, think about how much faster that is. And if to the ant, we're going super fast. We're just screaming down the highway, you know, burning rubber. But to us, it's just a normal jog, 1-2 miles per hour. But to them, it's ridiculously fast. And it's all about perspective and scale. So the larger you are, the slower, higher speed seem.
And Galileo is 23,222 kilometers away.
Yeah.
I just want to spend a few minutes addressing what came up in the last hangout with regard to Hector's calculations of the angular size of the ISS and the moon. I just want to share something with you here, if I can. Okay. All right. Anthony sent me a video of Hector's calculations, and this is about 6 minutes into the video. And I want to point out something that's really glaringly obvious, and both Miles and I suspected that this was the case. You'll see that he's used here a width of 108. I'll see if I can get my, yeah. You can see that he's used here a width of 108 meters for the ISS. He's used a distance of 410 kilometers for the ISS. He's used a distance to the moon of 405,367 kilometers, but he's used here the radius of the moon, 1,738 kilometers. He's used the full width of the ISS in his calculations, but he's used the half the width of the moon in his calculation. And so what he's ended up with is a ratio of 16.5, whereas it should be a ratio of around about 33. If you use the proper thing, he should have either halved the distance, the length of the ISS, or he should have used the full diameter of the moon in his calculations, not the full width for one and half the width for the other. And therein lies the error. I've actually done a proper calculation of all of these things. I'm going to stop sharing this now and see if I can get up my other calculations.
First off, 33 is an Illuminati number, so it's not real.
Yeah.
By the way, the moon is 384,000 kilometers away from the Earth, not this 410.
It depends. Well, no, it depends. It varies between about 356,000 kilometers and 410,000 kilometers, 408,000 kilometers.
You were just using
like that.
this big.
Okay.
Right.
Yeah, it varies quite a bit.
Yes, elliptical.
Yeah, I actually did some quite a lot of calculations on this last night, and here are my calculations. What I did was I used these figures.
We can't see anything. We can't see what you're doing.
Oh, hang on.
Oh, sorry. Oh, sorry. Can we?
Oh, no, I can see.
Sorry,
Yeah,
my fault. I've done the wrong thing. Sorry, my problem. Sorry.
You can see here all of the figures that I've used. They're all the figures that I've used in my calculations. That's the equation that you use up there to calculate the angular size. And I've done the angular size calculations for the sun, for a distant moon, a near moon, and for the ISS. And then I've got the ratios of each of those. The angular ratio for the sun is 34.98. The angular ratio for the near moon is 36.65. The angular ratio for the far moon is 32.13. And that doesn't take into account the angle that you're actually viewing the ISS from. If you actually do the calculations and take into account the angle that you're viewing the ISS from, you end up with a ratio of around about I think I've figured it out down here, you end up with a ratio of around about 41.24. Now, I looked at the video that Anthony was looking at, one of Red's Rhetoric's videos, and I did an actual analysis of it, and I enlarged it to the biggest I could on my screen, and I got a width of the ISS of about 8 millimeters and a total width of about 355 millimeters of the moon. And when you put that ratio in, you get those measurements in, you get a ratio of around about 44.4, which matches quite reasonably with the calculated ratio of that 41 or so that you expect to get. So it all ties in very, very nicely and works very well. So poor Hector, he just neglected to do one adjustment in his calculations. He forgot to halve the size of the ISS or use the full diameter of the moon, and that's where the problem lay. So I'm just going to stop sharing that now. Okay.
That was awesome.
I'm pretty sure you called that.
It
At
shows
the
you don't
time.
have a life, Paul, but it was pretty cool.
Yeah, that's right.
I'm pretty sure you pointed that out at the time.
was
Did you
awesome.
not, Paul? Yes. Was it today or earlier? I forget.
Who needs
Lose track
one?
of time. But I'm pretty sure you pointed that out at the time. Did you not?
No, I haven't talked about it in this hangout yet.
Not
That
in
was
this
the first time
hangout.
I've talked
When
about
the
it.
maths was first presented to you, there was some ambiguity about halving it, and I'm pretty sure you addressed it initially, from memory.
No, I don't think I did because I can't remember talking. I'm pretty sure I haven't talked about this at all. This
Maybe
whole
it
hangout.
could have been someone else.
Yeah.
Anyway, good time.
Yeah, I don't
Sorry, one more thing.
Anyway,
one more thing.
that's the
One more thing. Bear with me. We've been joined by Skyfly Bry. Get it every time. How you doing, Bry?
What's up, Skyflyer?
Hi, Nathan.
I'm happy to have heard that.
Good to have you here, Bry. Good to see you. Got about 10 minutes left.
indeed.
Just so you know, 10 minutes left.
I enjoyed that explanation, Paul. I hadn't heard that.
Yeah. This is a good hangout. This was a good hangout.
Oh, yeah. No.
After the hangout's finished, I'll put it back up on share if anyone wants to look at it in a bit more detail, how I did it.
Sure.
Okay.
I just hope it doesn't get put to the wayside, which I know it's going to be, but
Yeah. Okay. What next?
So Nathan looks well angry on his webcam. I think he's telling his missus how the flat Earth's getting wrecked.
I heard that the real Jaren's out there in the chat. That's pretty
real
interesting.
Jaren's in there along with the fake Jaren sock.
Shut off the show.
Jarenism. Oh, fun.
Definitely the real Jaren.
Got about 8 minutes left. Just so you know.
Baby.
That it works. Measurements to the sun or moon work on a flat Earth too. What's somebody like put that?
Your child is adorable.
I've looked at it myself. I understand it doesn't work. I'm probably not going to be the one to make the presentation, but I get it. I've looked at all kinds of different ways for this and know that it doesn't work. Does anybody have how do you explain it to a flat earther so that they can understand it?
That's the difficult part. So if you're watching, Anthony, I hope you got that explanation, and I hope you tell Hector in a sensitive way that he was wrong. Mistakes like that happen. That happens to the best of us.
he's young. He'll get over it.
That's
all
why
motion
corroborate.
must be observed. Hey, all motion must be observed. At some reference frame, it must be.
This is
Wow.
It's why corroborating your work has to be done so that other people can say, "Hey, we got it wrong. We got different results." So both of you do it again and see what happens the next time.
Yeah, but showing your work is
And
boring.
I know it's so boring, and then having a third person that each of you corroborate with, that's even more important.
And what do we
And a
call
fourth.
what do we call science that only relies on secondhand information and computer models? Junk
Well,
science.
I don't know
Junk
any science that does that, so I don't
Globe
know.
Earth science does. Globe Earth science does, and it's junk
Well, I
science.
mean, you're free to assert that if you like, but no one's going to corroborate that with you.
Other than the person already
not on
discovering
this
what isn't secondhand.
Secondhand information had to be first-hand information at some point.
Yeah,
Right.
by the person.
So you
It
can
could be.
you can make it firsthand information again by doing it
He
yourself.
just made a claim that it must be firsthand at some point. So was Santa Claus ever
Well, it
firsthand
is.
information? Was Tooth Fairy ever firsthand?
Yes, they were firsthand lies.
Actually, science.
Okay, Louis, I
We,
agree.
as we
Louis,
know,
that was honest.
as we know it, Santa Claus was actually the first.
So I mean, you can't demonstrate that any of the things like trigonometry, for example, like you can't demonstrate that that's a lie.
Have you, Sniper? Have you seen the whole entire Earth at once? Have you seen it being flat? Have you seen the dome? Have
You've
you
been to the
personally
sun?
experienced the dome?
Oh, Sniper's been removed. See, there's obviously a globe head Sniper, and it just makes you guys look bad because every time a flat Earth just gets removed out, like Truth Seeker or
Well,
Anthony Riley.
how do we know it was a globe head sniper?
Must be. There's no globe heads getting removed, only flat Earthers. So, you know, you guys are talking about first-hand information. None of you have been to the sun. None of you have been to the moon. You know, these are intangible objects that you have never experienced. What you are, hold on, Joseph.
Have any of us been to the North Pole?
What you are talking about?
You hold on, Nathan.
is
Have any of us been to the North Pole?
You're doing extrapolations. That's what you're doing. You're
Have
not having,
any
you're
of
not
us
having
been to the
first-hand
North
measurements
Pole
of the sun.
to
That's
determine that
nonsense.
Santa Claus isn't real?
Well, no, you're talking about extrapolations.
Okay, so then we can't know, can we?
You're talking about extrapolations. Nobody has first-hand knowledge of how far away the sun is. Nobody's gone out and then measured it. This is nonsense.
Right. Well, no one's
Talking about extrapolating
gone
the
out to the
information.
dome and that
Using the powers of deduction is not the same.
You should rewatch this hangout, Nathan.
First-hand knowledge doesn't mean that you have to actually go there. First-hand knowledge can be making observations from Earth.
Right, Nathan,
Making
it's like
extrapolations.
that's like saying
Extrapolations.
since you haven't been to the North Pole, you don't even know that the North Pole exists.
I
You
mean, how
haven't
many-
been to Canada, or you haven't been to, let's say, I'm assuming you haven't been to Israel. Am I correct in that? How do you know that it exists? How do you know anything that you? How do you know that the Earth
Easily verified.
is
Can
not
easily go there. Easily. Can't go to the moon. Can't go to the sun.
Okay, but you also can't go to the dome easily now, can you? Can you
How
go
about
to
the Marianas
Oh,
Trench?
what dome? I don't know what
Right.
you're talking about. What dome?
The dome
Dome.
that I say covers the flat Earth. No,
Right,
none
so
of
do you
you've been there,
concede
so
that none of us
you
have been
can't
to the
say that it
sun?
exists.
None of us have got first-hand information of that. We can't get that.
Well,
we
we have
have
been
to
to the moon.
extrapolate it, correct?
We do all have.
So that's clear. None of us are going to be measuring these. None of us are getting
But
accurate measurements
you're
of
also
these
dodging my
intangible
question.
objects.
Have you been to the dome over your flat Earth?
What
Yes
dome?
or
I
no?
don't know what you're talking about. We're not talking about any dome. We're talking about the sun and moon, which are intangible objects none of us have been to. We have to make extrapolations and theorise.
Nathan, you seem to have this misconception that first-hand information means you have to go there. That's not true. You can collect first-hand information without going there. You can make observations. You can
you
do
can make measurements of
and
the
not
angles
necessarily
first-hand.
have to be there.
Yeah, you
Go
can
there.
make first-hand
That's first-hand
observations and make
information as well.
extrapolations from them. But it doesn't mean that we have been to this intangible object and actually verified that it is those distances. We haven't done that.
Nathan,
and we can't do that.
When you use the words, I have no firsthand information of something, what you really mean, what that actually means is that you have not done anything that would corroborate what others have told you.
What, like tracking the sun, for
I have
example?
never-
Hold
I have
on,
never
hold on,
been-
Joseph. Like tracking it, for instance. Have you done
Nathan,
that? Hold on, Joseph. I'm just addressing something Lewis said. So, like tracking it, for example, Lewis, have you done that?
I didn't hear you.
Tracking the sun, for example.
Jacob, come on, or Joseph, come on. I didn't hear him that time either.
Yeah, Joseph just can't seem to keep his mouth shut. So, have you
Oh,
ever
he can.
tracked the sun?
Have I ever what?
Tracked it. How many times do I have to say it?
Sure, I've tracked it.
All right, tell me all about it.
It moves across the sky.
Wow, that's so fantastic. So you're
I know,
asserting that I've done
It's just
nothing.
like my
You're
answer,
asserting
it's
that
just
I've done nothing, and what you have done
it's
is
just
tipped
like
your
my
head.
answer for
You've
trigonometry,
changed the angle of your neck. Wow, Lewis, you're an amazing credit to the globe head side.
Right,
You've
and what it
moved your
means-
neck a few degrees. You are sensationally talented.
He did trigonometry. Lewis did trigonometry.
No, Nathan.
Yes, we've already gone over this. He can do an extrapolation
I know.
using maths,
I
and
know.
he can get
What have you
first-hand.
done,
He can get
Nathan? What have
first-hand
you
measurements
done?
of the angles.
No,
doesn't mean he's
look,
been to the sun.
You
Doesn't
didn't
mean he's been
actually
to the
address
moon.
what I said, Nathan. I said when somebody uses the term, I have, or the phrase, I have no firsthand knowledge of something. All that means is that you have not actually done anything to get firsthand knowledge. That's what it means, because firsthand knowledge is your experience. That's what it is. Secondhand
None of us
knowledge
can
is
get first-hand
somebody else
knowledge of the
telling you
sun
about their firsthand knowledge.
in
That's
terms
what
of its
secondhand knowledge
distance.
is.
Are we ever going to get first-hand knowledge of the sun's distance?
If you do it,
Go to it.
yes. If you go make observations, then that is
No.
firsthand
We to verify
Absolutely.
to verify
yes.
those observations.
Yes, the best you can do, Nathan, is
the
get other
best
people
we
to
can
get-
do.
the
See,
best-
there's a good
Nathan,
saying
the
from
be-
The
Nathan,
Rock.
Nathan, just relax.
There's a
The
good
best you
saying
can
from The
do
Rock. Let's
is
tear you
get
down,
other
so I don't have
people-
to talk over you loud. Losers always whine about their best. Winners go home and fuck the prom queen. And with that, I will say a massive, huge, enormous thank you to all of the live audience for joining us on this debate. And also, of course, a massive thank you to all of the panel for making this debate possible. Be sure to like, comment, share, and subscribe. I've been Nathan Oakley, and I'll see you all in the next video.